I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I have very little time today, so I'm just going to work a little bit on this paper. I just finished converting the main proof here into a proof by mathematical induction. Now let's add a section about the dual Knight-Darwin law. The dual Knight-Darwin law, one form of it already appeared in my 2013 paper, Infinite Graphs in Systematic Biology with an Application to the Species Problem. The Knight-Darwin law says that in any infinite chain of parent-child, child-child, etc., there will be vertices with multiple parents. The dual Knight-Darwin law says that for certain such chains or under certain such conditions, there will necessarily be a node with multiple children. Yeah. Well, what do we need? We just need the IAP property, I think. Well, do we need convexity? I'm not sure. Let's just start, and then as we need things, we'll add hypotheses as needed. And I'll insert narrative around this theorem later. Dual Knight-Darwin law. Suppose S subset G satisfies the IAP axiom. If S locally satisfies the Knight-Darwin law, then S locally satisfies the dual Knight-Darwin law, which we should define. S subset G is said to locally satisfy the dual Knight-Darwin law if the following: if for every infinite directed path u1, u2, dots in S, there exists some I such that ui has more than one children in S. Now, proof of this dual Knight-Darwin law. Let u1, u2, dots be an arbitrary infinite directed path in S. We must show that some u sub I has more than one children in S. Now the idea here is that by the Knight-Darwin law, you can get a bunch of second incoming nodes. By repeated applications of the Knight-Darwin law, there exist I1 less I2 less ... such that each u sub I sub j has more than one parent in S. Using the axiom of choice, for each I, let y sub I in S be a parent of u sub I sub j other than u sub I sub j minus 1. Now, of course, if in standard biology, an organism would never have 3 or more parents, so the axiom of choice would not be necessary in that case. But we have not actually assumed that. So a priori, organisms can have more than 2 parents. Perhaps it's worth writing a note to this effect. It would probably be best as a footnote here. If, as is generally assumed, if as would be consistent with the biological nature of G, we assume that no vertex has more than 2 parents, then the axiom of choice is not needed. For each I, let yi in S be a parent of uij other than uij minus 1. Now, the idea is that now, since U1 has infinite many descendants in S, namely U2, U3, ... the IAP axiom guarantees that S has less than infinitely many non-descendants of U1. Since the set y1, y2, ... since that set has infinite cardinality, there must be some k such that u sub such that y sub k is a descendant of u1. Thus there is a directed path x1 ... xn in S with x1 equals u1, xn equals yk. Now we're going to need the convexity property, so let's modify this there and say if S, let's say suppose S satisfies the convexity axiom and the IAP axiom. Now, by convexity, each x, we've already used I, each xl is in S. Now, since yk is different from u sub I sub k minus 1, the path, the finite directed path x1 ... xn must be different from the finite directed path u1 dot 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 u sub I sub j minus 1. Case 1. x1 dot 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 xn is an initial segment of u1 dot 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 u sub I sub j minus 1. Then since the two paths are different, so thus, just so the reader better understands what's going on, x1 equals u1, x2 equals u2, dot dot dot, x sub n equals u sub n. Since the two paths are not the same, u sub n is not the final vertex in the path. Oh, wait, what? U sub I sub j minus 1 is not the final vertex in the path u1 dot 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 use that's equal to, wait, not xn equals that, but rather x sub ij minus 1 equals u sub ij minus 1. Since the two paths are not the same, u sub ij minus 1 is not the final vertex in the path. Or, well, let's say x sub ij minus 1 is not the final vertex in the path x1 dot dot dots xn. Rather, thus xn as a child xn minus 1 or xn plus thus xn wow, time really flies when you're having fun. Already down to about 7 minutes before I have to go. So the two path x1 dot 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 xn is a path which goes from u1 to yk. Let's just say, but for now let's just say this implies, and I'll fill in the details later, that xn equals y sub k has some child this implies that x sub ij minus 1 has some child z, which is an ancestor of yk, by the complexity axiom, Z and S. Thus, x sub u j minus 1 has two distinct children, x sub u j and z, both in S. And we need to ensure that z not equal to x sub u sub j, which we can do certainly, but I don't have time to fill in the details right now. Case 2 is that x1 dot dot xn is not an initial segment of u1 dot dot u sub s of j minus 1. So then we can let L be minimal such that x sub L is not equal to u sub L. And this will be L as the rank to n. And then well, that means that okay. Since x1 equals u1, L is bigger than 1. Thus, x sub 1 has two children, namely x sub 2 and u sub 2. Sorry, thus x sub L minus 1 has two children, namely x sub L and u sub L. Different by choice of L. And furthermore, x sub L is an ancestor of y sub k y sub k is an S, right? Where do we first define y's? When we define the y, yeah, it is an S. So by the convexity axiom, x sub L is in S. Thus, thus u sub L minus 1 has two distinct children in S as desired. Now, yeah, that's all we needed to do. Yeah, QED. And that's a fantastic stopping point. I'm about out of time. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. And